Welcome, everybody, to this webinar on on-prem and air-gapped AI in manufacturing and logistics. Really excited to share the day with you, to hear your questions, to hear the discussions and the comments that you might have, and to provide enough time for those questions. We're going to jump in here in just a second, but just by way of logistics, want to let everyone know that there's two ways you can ask a question. So you can ask your question in the Q&A panel within Zoom, or you can just paste it into the chat. Sharon, who's one of our AI engineers here at Prediction Guard, he's going to be monitoring those, and then at the end of the conversation, he's gonna feed me some questions, some curated questions, synthesized questions that we can answer at the end. If you don't get your question answered, don't worry, we can always follow up. I'm gonna provide my contact information and all of that good stuff. So thank you so much for taking time, and let's just go ahead and jump right in. Let me share my screen. All right. Okay, so today is all about on-prem and air-gapped AI. I think generally that is applicable, regardless of whether you're working in manufacturing or logistics or transportation. This is relevant and increasingly a trend that we're seeing at Prediction Guard is people wanting to almost revert to pre-cloud era and run AI systems in on-prem scenarios, whether that be a big workstation that's sitting in the corner of your office or a data center that you have on site. So yeah, excited to dive into a little bit of that just by way of context in terms of why we're talking about this. Prediction Guard is really all about, a couple things. The main thing that Prediction Guard does is provide secure private AI systems for companies operating in regulated industries or with security sensitive use cases. And of course, in manufacturing and logistics, if you're working in those areas, often you are working in constrained environments, in air-gapped environments, maybe working with infrastructure that's set up at a manufacturing facility. And so we're working with a number of customers on AI use cases in these different areas. Just to highlight one of those, recently we've been working with Purdue University. They have a new institute that's spinning up over there related to AI in medicine manufacturing and how AI can actually improve resiliency and transform the manufacturing of medicines and actually onshore a lot of those things that are right now maybe considered a national security threat. Here you can see the president of Purdue talking about this effort and how hopefully this is a transformational effort. And we're providing the kind of secure private AI system underlying that effort over at Purdue. Along with that, we love all of our team, whether it's myself or others in our team, love engaging in the wider conversation around AI security and privacy. Myself co-hosting the Practical AI podcast and occasionally teaching at Purdue. And then members of our team that are participating in committees and benchmark studies with OWASP and ML Commons on this subject. But it's really these sorts of scenarios like I talked about that are driving how I'm going to talk about air-gapped and on-prem AI today. Those like the one at Purdue where they're talking about the manufacture of medicines. Here you can see a lyophilization process, which is basically the dehydration of drugs into a stable formation that can be shipped out as part of the manufacturing process. And a lot of these, you can see equipment here. A lot of that equipment drives data that goes into various software platforms. But eventually, the goal with the institute that we're working with is actually building resiliency in a number of areas with AI that's plugged into both that process or equipment data, but also helping operations, supply chain, and other things. And in particular, in this sort of environment, when we're talking about pharma companies, we're talking about very sensitive IP often, and sometimes data that is sensitive in other ways, like clinical trial data, other data like that. It is imperative that this is private and secure. This isn't data that you would just sort of send across the internet to third-party AI systems like OpenAI and Anthropic. This is data that you want to have tight controls over and that you want to have auditability and security and safeguards in place. So that's all context just to give you a sense of our team, what we're involved with, and how this is really informing how we think about on-prem and air-gapped AI systems. Now, I do want to inspire, based on some of the use cases we've seen across different customers in manufacturing, I want to just give you a little bit of a sense, a few use cases that you can have in mind as we dig into the more technical aspects of these systems. But at the application layer, you might think of example AI applications in manufacturing and logistics, like a preventative maintenance assistant. So this might be an AI system that automatically monitors and analyzes machine data or equipment data, monitors for anomalies, maybe analyzes that data and actually provides natural language instructions for maintenance individuals or summaries for triage, that sort of thing. Those are all things that we're seeing. You could also think about document intelligence, searches across complex manuals or SOPs, extracting key information from those documents. Often there might be, process plans or manuals for certain equipment that are very complicated, hundreds of pages long, and need a way for this dynamic, fast search to be a part of the process. I mentioned also supply chain. This doesn't have to be necessarily related to the actual processes of the manufacturing. This could be something related to raw materials or supply chain, actually monitoring for disruptions in that supply chain or changes in pricing, changes in lead time, alerting the relevant people, creating actual strategy documents or briefing documents based on certain problems in supply chain. Again, something that we're seeing. But this is only a selection, just to give you a little bit of an idea of the types of use cases that we have in mind when we're talking about AI in the context of advanced manufacturing and logistics. It's these types of use cases that we have in mind. Now, people working in manufacturing and logistics, just like in any industry, are going to use generic tools like a ChatGPT or Copilot, more likely. But these sort of systems are very verticalized, custom AI integrations. And that's what I want to focus on today, is your company, your manufacturing company, or maybe a customer that you're serving in this industry. They're likely going to build value with AI by not only using the generic tools like a Copilot or something like that, but actually creating vertical AI agents or very domain-specific custom AI applications like these that I'm describing here. And the systems that we're going to talk about today in terms of deploying on-prem and air-gapped AI enable those sorts of verticalized or customized systems. So that's what we have in mind. Okay, so let's talk just a little bit about what a typical AI system, when I'm using this term system, what that actually looks like. It may be tempting to equate this to a model, right? You might think, oh, how do I get a model into a manufacturing environment that's on-prem or air-gapped? That's kind of part of the question that you should be asking, but it's only a very small piece of the overall system. The use cases that I'm showing here related to this, preventative maintenance assistant or document intelligence or whatever it might be, those actually require more than just a single model. They require a system of things working together. And so when you're talking about deploying this sort of intelligence in that environment, you actually want to think more systematically. What are all the things that need to be working together for us to have a capable and full-featured AI application in an on-prem or air-gapped scenario? So let's start at the bottom. So there's certainly a model that you need. Now, you may be thinking, okay, I can deploy a language model like a llama model or a Quen model or something like that. I can deploy that with ollama on a single VM or on a bare metal machine, no problem. And you're right, there are a lot of tools that allow you to run local models quite easily. The issue with that is that number one, often for these sort of full-featured AI applications, you don't just need an LLM. You might need a vision model, you need embeddings, you need re-rank, you need document extraction, safeguards, all of which are model-based things or models themselves. And so actually what you end up with is a kind of set of components that are model based, not just a single model to enable these full featured workflows, like the preventative maintenance thing or supply chain assistant. So number one, you sort of need more than the LLM. Number two, when you deploy something with one of these local tools, often that tool is meant for kind of your single user usage. So I can deploy a model on my laptop. That's great. I can use it locally. I can use it privately. Wonderful. But you're really not going to run your enterprise application off of the model running on my laptop, right? You somehow need horizontal scalability. You need to potentially distribute load across multiple replicas of these models to have high availability. And so really, I want you to think when you're thinking of, deploying the model layer of your AI system in an air-gapped or self-hosted scenario of any kind, that you're going to be dealing with multiple models, and you need to be able to handle the scaling of each of those multiple models. Now, then above the model layer, you're going to have an application or tools layer. So you may have a custom tool that you've built or that you've customized, like one of these sort of supply chain assistants or regulation assistants or whatever it might be. That might be a custom app that you have deployed in your own infrastructure to support your operations. And those custom apps are going to have model interactions, text completions, embeddings, etc., down to the model layer. You may also deploy a set of AI tools that are pre-built, so something like a Langflow or Open Web UI or whatever tools might be relevant for you to use that are already built, low code, no code builders like Langflow and that sort of thing. You could deploy those, but those will rely on you having a solid model foundation that can plug into those AI tools to actually give them the functionality to build the flows and the automation and that sort of thing. So you've got this application tools level, and then you have a data level or a data part of this system. Now, you may have an existing system like an MES system or an ERP, something like that, that already has data in it. And so that may already have a database that's relevant for you to pull data out of or interact with. Maybe you have an object store that contains files and that sort of thing. But in addition, whether it's an existing database or not, you need to have some database that supports vector operations. So if you're not familiar with vector databases, this is a key component of this system that allows you to do semantic search over text and other types of data like images. So this allows you to get a user question like, hey, what's our SOP for X? And then you can search based on that text in a fuzzy way, your vector database to retrieve relevant documents relevant to that question about SOPs or whatever it might be. So these are all, I've kind of split these down into what I would view as kind of a minimal kind of full featured system with these required components, and then some other optional things that you might see as part of your AI system. But again, critical to think about this as a system, not just a model. Okay, so in order to talk about how we are deploying some of these things in air-gapped or on-prem scenarios, we also need to just break down how these different workloads operate, just to get a common understanding for the different components of this AI system, because there's sort of a variety of concerns with each of them that differ one from the other. So in terms of the model itself, and this would be true for any of those model-based components, whether it's a language model or a vision model, or an embedding model. Somewhere you're going to have a server or a VM, depending on how you have your on-prem environment set up. You're going to have a server. You're going to need to have model serving code. Now, this can likely be a generic sort of model serving code if you want to use something like VLLM. In Prediction Guard, we use actually a variety of model serving frameworks depending on both the underlying compute resources, whether it's CPU or GPU, and a number of other constraints. But you're going to have this model serving code that somehow needs to get down to the server. You're also going to have these model components. Which somehow need to get down to the server, likely to a local cache on the server. And so this is where I really want to emphasize it's sometimes confusing what people mean by a model and what exactly needs to go to your environment to run in an on-prem or air-gapped scenario. So let me actually give you an example of this. So here, I said, this is my model. It includes a set of model parameters and model code. If you're not familiar, Hugging Face is kind of the typical place. It's kind of the hub of all AI models and data sets and other things. And so if I look at a particular model that I might want to use, like, the latest release of DeepSeek R1, which may or may not be the best model for you. But if I look at that, I can actually see in the files here, there's a set of files that include all of these, 4 to 5 GB files. These correspond to the model parameters of that model, all 600 billion of them, or however many model parameters there are. Those parameterize the model function to perform the given data transformation. So, for example, in the DeepSeek model, it takes text in and then it predicts text out, and it needs to be parameterized with a set of parameters. And so you need these model parameter files to parameterize that model. But you also need model code to load and deserialize those parameters and to actually execute the functionality of the model. Now here, for this model, you could run it, for example, with the Transformers library. This is an open source library that will run this model. It's not the only library that might run this model, but it is an example of the code that you would need to actually run the model. So hopefully that clarifies what we mean by model, and also for these model components for each of them, for the LLM, the vision model, the embeddings, the safeguard, if those are model based, you're going to need a server somewhere that has model serving code. You're going to need to load those model files in, deserialize them, and serve them from that model serving code, often via REST API. At the next level, we have the applications or tools. This might be, for example, your agent to help out with supply chain alerts, or your assistant over documents or SOPs, or whatever that might be. In this case, often these run on just CPUs. And this is standard kind of application code. So it might be an API, or it might be an API and a UI, or a single UI. Whatever it is, it's Python code or JavaScript code or .NET code, whatever that custom AI application is. There's going to be that code that's served off of a commodity CPU type of instance. And likely that's going to have some local storage of data in a cache or logs or something. But it's also going to interact with external things like the REST API to the models to do those model interactions, or structured queries to data sources or databases. So here, the compute side is a little bit easier. The loading of data is a little bit easier in terms of the model, but you do have these external connections. And by external, I mean external to the application or tool, not necessarily to the environment. Like if it's an air-gapped environment, obviously there's no external connection. Okay, let's talk about the last of these components that might be unfamiliar to you. These would be vector databases. And similar to any sort of database of any kind, whether that be a SQL database, relational database, document database, vector databases come in kind of two flavors, two main flavors that might be useful for you to know about. One of those is a client server type of architecture. So this would be where you actually are running a process on a compute node, a bare metal server or a VM that is the database server. And that's the server side that actually connects to the persistent storage of the database and allows you to query the data in the persistent storage. And then you have your own application code, which imports a database client and then connects to that database, which is always running in the background. So this is client server type of architecture. And then there's a serverless or embedded version of this. There's many types of databases, obviously, and this is just a single binary distinction. But in the serverless or embedded case, you have persistent storage of the data, and often, an on-disk index or something like that that's saved in that persistent storage. And you don't need the server component or the always up database server component to query that storage. You just query that from the application code with the database client directly to a connection to that storage source. So these are serverless embedded options, client server options. If you're curious about this, there's a really great blog called the Data Quarry. Um, and this is from Prashant. He does an amazing job at a lot of different blog posts, but actually, you'll see that he has a set of blogs about vector databases, and there's actually 4 of these vector databases blogs. And he goes through all of the different things that you might want to be considering when you're choosing a vector database, including this distinction of client server architecture and serverless or embedded. The reason why I mention the serverless or embedded piece is that in our experience, when you're deploying to manufacturing logistics environments that are air-gapped or on-prem, it's much easier to utilize these sort of serverless or embedded databases, which can actually scale well because it allows you to run one less process as a part of your system, right? You can just focus on your application code and then connect to the storage source. We typically utilize LanceDB in our applications. It's an amazing database that it's vector native and works serverless. Just a plug for them. Okay, so let's move on from the kind of components here to the architecture that we use for deploying an AI system privately and securely. I'm kind of pulling back the curtain a little bit and giving you a sense of how we do this and how we think about it. And some of this may not be surprising to some of you, but I want to give you a real sense for how we're doing this. And that's kind of in the following way. So just breaking down this picture a little bit differently, you will have your compute, which may be everything from a single CPU node to a big cluster of GPUs, depending on your scenario, how many resources you have, that sort of thing. But somehow you're going to have that compute and you're going to have storage, persistent volumes of some type. On top of that, how we are managing the deployment of all of these apps and tools along with our AI system is all containerized and it all runs in Kubernetes. If you're not familiar with Kubernetes, it's a way to orchestrate the running of software containers across a set of compute resources. And if you think about, again, think about your AI system as a system, not just a model, you're going to need to have that LLM vision model, embedding, re-rank, safeguards, applications, tools, vector database, etc. So you want a way to orchestrate the deployment of all of those things in the compute that you have available. And we do that through Kubernetes. Prediction Guard runs on top of Kubernetes, and you can actually trigger the deployment of these things in underlying. When you trigger something in Prediction Guard, it actually calls into Kubernetes and makes the changes to your cluster. A couple of things to note here, just as you're thinking about this in your environment, though, is that this allows us, you really want to think about the isolation of these AI system containers away from the application layer as a separate set of containers that have isolated networking. We very frequently get asked, well, hey, you might be running a Quen model or a DeepSeek model. How do I know that the model builders back in China aren't getting the data that's running through my model? And the answer to that, in terms of how we set up our system, is that we isolate those AI system containers, the ones that are running the models. We isolate the network so that those containers can only talk to the application or tool level containers. And so there's no searching of the internet, there's no phoning home, anything like that from those AI system containers. Now, obviously, your application containers may need to interact with users that are directly using those tools or equipment or other services or servers in your infrastructure. And you can set up the firewall accordingly for those applications that have external to this system connections. But in that case, you can leverage great things like your existing SSO or role-based access control, et cetera, to secure that application layer as you connect to various other or other things connect into your applications. Okay, so finally, let's talk just through kind of some of the pro tips that we found for deployment of these sorts of systems that I've just described in these kinds of environments, air-gapped and on-prem environments. And let's do a first or a first point of differentiation here between two scenarios that you might see. You may see a scenario, as I mentioned before, of a kind of heavy edge node. And what I mean by that is, let's say you've got a beefy workstation, it's running at your manufacturing facility on the floor, right? Or in someone's office or wherever it might be. And you need to deploy all of what I've just talked about on that single node environment, meaning there aren't multiple different servers or VMs. It's that single node. You need to deploy both the applications and tools, the AI system there, and the persistent volume, or connect to the persistent volume there. The other scenario that you might have is, oh, we have a data center, right? We have equipment on site at the manufacturing facility, or we run our own infrastructure as part of our logistics operation. Here, you will have multiple, servers and VMs, and you will need to run an orchestration layer on top of those, like Kubernetes, to run and actually schedule your applications and your AI system across those servers and VMs. Now, here's where get to a couple of the pro tips that I'd like to share with you today, and happy to go into more detail afterwards. Whether you're doing the single node deployment or you're doing the distributed system deployment, again, I would encourage you to isolate the networking of those AI components, especially if you're using models or model serving code that you haven't scanned for security vulnerabilities or done static analysis on, or you don't fully know what the implications of that are. Just isolate the networking of those components so there's no question where data is flowing. And then you can set up, again, the firewalls and the external access to those AI apps and tools using least privilege sort of principles and maybe existing SSO or role-based access controls. Now, in the single node environment, what we're doing in these cases, because again, we're still orchestrating the deployment often of multiple components that all have to work together as an AI system, we're still using Kubernetes. It's just we're not using kind of the full-blown full Kubernetes. We're using a lightweight version of Kubernetes called K0s. So if you just search for that, you'll see this is a Kubernetes distribution meant to run, on-prem with zero dependencies. This is a great system that allows you now to port into a single node environment, have no dependencies, but still orchestrate the deployment of multiple workloads on that single node. Um, I would also recommend that you look into model optimizations because all of these models will be running on a single node, and there will be limited resources available in that single node. It is helpful if you can run at least as many of those components as possible on CPU, not on GPU. Often this is what you will have access to. Now, maybe you do have a heavy edge node with a GPU on it, but you won't be able to probably schedule all of your workloads on that GPU. So considering model optimizations like quantization or other model optimizations, rather than the kind of stock model that comes from the model builder, but looking into those quantized model versions of the models can be very helpful. On the distributed system side, yeah, I would encourage you, create those node groups for CPU and maybe accelerator nodes. That way you can schedule specific workloads on GPU nodes and others you can kind of horizontally scale across CPUs. We've actually had a lot of really good success with taking a model that's either quantized or a smaller model and then distributing that horizontally, not across big expensive GPUs that you're going to pay 60 grand a month for, but across either commodity GPUs or across CPU nodes in the cluster. And this allows you to kind of have a bit more throughput and support concurrent users in your system, but also not pay out for just big, beefy GPUs, which are very scarce and very expensive as a result. So yeah, would encourage you to think about that sort of horizontally scaling over CPUs as well. The next kind of set of scenarios that you need to think through is connected versus air-gapped. This audience, you might already understand the implications of this, but just to make it clear, in the connected scenario, we're talking about a scenario where at least you have access to the public internet or at external systems during the install phase of the system. Now, you may shut it off after that, but you at least have the chance to have those connections externally where you can get those model parameters, you can get code, you can get updates externally. In the air gap scenario, right, you have to bring everything into that environment. There's no way that you can connect externally to get updates, model parameters, etc. So in either of these cases, I would definitely consider kind of having a local model cache or vault. If you're using the Hugging Face system, it does actually create that local cache and you can manage where that is. And that's going to allow you to fill that local model cache. And regardless of whether you have access to the internet or not, it'll prevent you from downloading things from third parties over and over. And in the case where you don't have connection, you can import that model vault maybe to a machine. I would also prioritize these sort of serverless vector databases because rather than having to deploy a whole client server architecture for your vector database, if you're using something like a LanceDB or even a DuckDB that is embedded and serverless, you can transfer files and essentially move around your vector database as a set of files, which fits this air gap scenario. On the connected front, we would encourage you, even though it is connected to whitelist appropriate trusted sources for model artifacts. And in these cases, often you can use Helm or something like that to pull images for your AI components and your applications from container registries. Whereas in the air gap scenario, really you want to create zero dependency bundles to ship to the environment. You want to bring those in and actually maybe create for your AI components, create AI components that have the model files already bundled in, those parameters in the model code. That way, you don't have to, again, connect to an external registry. What we do is when we ship those images in, we actually ship them with an install bundle that has zero dependencies, such that when we spin up K0s, for example, we can have those then registered in a local registry from those containers, and then update those containers over time with the that are in the local registry.